Welcome to the video on partial fractions decomposition. First of all, what is it? To answer that, let's consider this problem. Suppose we were adding these two fractions. Well, because the denominators don't match, we'd have to come up with a common denominator. Here's the work shown to get a common denominator. I won't belabor this point because it isn't the essential idea in this video, but the point is, if you were to do some algebra, feel free to pause at this point and examine the work. If you were to do the algebra, you would have combined two fractions into a single fraction. Now these expressions are equivalent. The top and bottom expression on this page would have the same value, despite their different appearance, no matter what x were. And this process of going from multiple fractions added together into a single fraction is called combining rational expressions. That's something you've seen before, chances are you have if you're watching this video. But that isn't what we're doing in this video. We're going the other way. In other words, we'll be given the expression at the bottom, a single fraction, and have to decompose or break it up into the sum of two or more fractions. That's called partial fractions decomposition. Here's our first example. Step one in partial fractions decomposition is to factor your denominator, because each of those factors is going to lead into the decomposition setup. Notice what I've set up here. I've used the symbols a and b to represent numbers I don't know. But notice what I'm saying here is because I have these two factors in my denominator, that when I decompose it, I'm going to get a fraction with each of the factors from the original denominator in it. In other words, use the denominator factors as a means to break it up. Now, the question we're trying to answer here is, what number would A have to be, and what number would B have to be for this to be a true statement? Now, it's a very messy equation to have to deal with, so mathematicians have invented a very nice trick called clearing fractions. What you do is you multiply the entire equation by the original denominator. Now, what this video doesn't get into is how when I multiply by x minus 4x minus 1, I get this result. I highly recommend that you hit pause and examine the details. So, now that we've done that, I'd like to warn you about a potential pitfall that you may or may not encounter depending on the problem. Notice that in the bottom line here, the a is the coefficient of the x minus 4 factor, and the b is the coefficient of the x minus 1 factor. And compare that to the line above it. You might be tempted to think that there's some crisscrossing going on here. In other words, that there's somehow some diagonal movement. And I assure you that is not the case, although it does seem to have that effect from time to time. If you're not sure how I cleared fractions and got this, take some more time and figure it out. It's essential that you figure out your algebra before you move on. But that's not the focus of this video. The focus of this video is how do we go about finding values for a and b that are going to make this a true statement? Well, there's a really nice trick that mathematicians have come up with. And they've discovered that you can plug in random values of x in order to solve for a and b. So what I'm going to do is I'm going to plug in x equals 1. Now it's important to notice here two things. One, you can literally choose any value for x, and this trick will work. But I recommend picking values for x that will make the algebra easier. So for example, if I plug in x equals 1 into this equation, I'm going to get this. And notice I have a b times 0 at the end of this expression. Therefore, it's very easy to go ahead and solve for a, because by a suitable choice for x, I've canceled out the b term. Did I have to choose one? Absolutely not. You can choose anything you want. But I thought 1 was a good choice because of the simplicity that it provided me in my algebra. Next, I'm going to plug in 4. You'll notice when I take this equation and I plug in 4, I get an a times 0 as one of my terms. And since a times 0 is 0, this becomes a real easy equation to solve for b. So I've now solved for a and b, which in some sense was my original goal, because my decomposition now becomes this. Now I'm done with this problem, but there's one thing worth noting. If I had chosen really strange values for x, say 2 and negative 5, I would have gotten a much different looking algebraic system of equations. In fact, if I had made, let's say, bad choices for x here, I would not have been able to solve either equation for a or b directly. However, putting these two things together as a system of equations would have allowed me to solve that system for the same a and b that I got when I used clever choices for my x values. It's also important to point out here that we're not solving for x. What we've done here is we've taken the original expression at the top of the page, turned it into the highlighted one at the bottom, and these two expressions are equivalent, meaning any value of x I would plug into both of them would yield the same result. So I've decomposed the top of the page into the expression at the bottom of the page. By the way, sometimes you'll see them written in slightly different formats. I would encourage you to compare those two and convince yourself that they're algebraically the same. So let's look at another example. Here's the 4 steps that we used on the last problem. But there's actually a step before that. It's the long division step. Why didn't we use it on the previous problem? Well, because you don't need long division whenever your denominator has a higher degree, which it did on the previous problem. But notice here the degree of the numerator, third degree, is higher than or equal to the degree of the denominator. So what you have to do here is you have to do long division before you can start this process. Now this video is not about long division, but I've made videos on long division, and if you feel like you need a review on that, check out my YouTube channel, Recidlo Math, and go to the long division video. But for the purposes of this instruction, we're going to assume that you either can or will figure out how to do long division. Feel free to hit pause, of course. Once you've done this long division, what we've done is we've decomposed this into the sum of a non-fraction plus a fraction. So in some sense, we've started the decomposition already. What we have to do now is factor the denominator, but we're only going to concentrate on the fraction part. We've already decomposed the 2x plus 8 part. Now we're going to break that fraction up. Now notice the denominator here has like factors, x minus 2 times x minus 2. And whenever that happens and you set up your decomposition, the strangest thing happens. One of your denominators is the same, x minus 2 squared, you'll see it under the b, and the other one is the linear factor inside the exponent. Why is this the case? Why are we breaking this up into two fractions, one of whose denominator is squared and one of whose isn't? Well, why and when are two different questions. When do we do that? When the original denominator has like factors, x minus 2, x minus 2. Why do we do that? That's a very long and interesting story that we won't get into in this video. The important thing is that we've set up our decomposition with one of the denominators squared and one of them not, because that's how you handle like factors. So next what I'm going to have to do is clear my fractions to find out what a and b are. So to clear fractions, I multiply the entire equation by the original denominator. You may want to hit pause and convince yourself of the algebra that you see here. Now, once we've cleared fractions, we plug in any x values whatsoever we like. This is the cool trick mathematicians invented. So what I'm going to do is I'm going to plug in 2. You don't have to plug in 2. You can plug in anything. But by plugging in 2 into this equation, I get a times 0 as one of my terms. And a times 0 is 0, and a little bit of algebra here shows that it's super easy to solve for b. Once we've solved for b, we have to still complete the task of solving for a. All right, well, let's take the equation and plug in 99. By the way, you don't have to plug in 99. I'm choosing 99 to show you that any number would work. I don't recommend you choose large 2-digit numbers. Totally up to you. So I'll take this equation and I'll plug in 99. And notice on the previous left side of this table, I already knew that b was 16, so I'm going to plug that in as well. Now this equation looks messy, but it ultimately does lead down to 24. Was plugging in 99 the best idea? Absolutely not. Would it have worked if I plugged in anything else? Yes, it would have. Now, this is the final decomposition here. Now look all around the page and piece all this together. I've taken the 2x plus 8 from my original long division and combined it with the decomposition from the fractional portion that was left after long division. Now I have a final decomposition for the original problem. Here's another example. I'm not going to do long division because the denominator is third degree. You can see if you multiply the denominator out, you get a third degree polynomial. And the numerator is second degree, so I don't need long division. And I also don't need to factor my denominator because in this problem, that's already been done for me. So I'm going to go to the next step. I'm going to set up my decomposition. Now here's a new thing, just to hit you up with this. I've broken this up, but using each of the factors as a new denominator in my decomposition. But here's what's new. We have something here called an irreducible or non-factorable quadratic. You can't factor x squared minus 3. And whenever that happens, the numerator above it is not just a single letter, i.e. a constant. It is a linear function. You can use ax plus s, you can use mx plus b, or fx plus w, or anything up there. It doesn't make any difference what you use as your constants. But whenever you have an irreducible denominator, quadratic in your denominator, then the numerator has to be linear. You might as well use mx plus b if you like. Now, I'm going to clear fractions, so I'm going to take my equation, and I'm going to multiply the whole thing by the original denominator. Again, hit pause and convince yourself this would be the end result. Now, I have to find t, a, and s to have a completed decomposition. So I'm going to plug in values for x. First, I started with -1. -1 happens to make the equation above very easy to deal with because of the x plus 1 factor in there. So when I plug in -1, I end up with t equals 2. Now, none of the algebra is shown here. You may want to hit pause, plug in -1, and convince yourself that t does in fact equals 2. There's a boatload of algebra not shown here. Then I decided to plug in 0. Now remember, you can plug in anything you want. There is no right or wrong plugins. But I thought 0 would be nice because then I would have an a times 0 in my expression, and that would cancel out the a. Now I didn't show a lot of the work here. And again, you may want to pause your way through this video. I'll stop saying feel free to hit pause, but there are lots of moments where algebra is omitted. But the bigger picture needs to be maintained here. The point is I picked a number for x, I plugged it in, and I found s. And then I picked a number for x again, and I plugged it in, and I ultimately found a. So it's hard when you're watching this video for the first time, presumably you're new to this. It's hard to get a sense that, well, what should I plug in for x? anything that causes a cancellation is a good idea. -1 was a great idea because it canceled out the whole last term of that middle equation there. And 0 was a good idea too. So be clever about your choices for x, not because you have to be clever, but because it'll cut down on your work. This ends up being the final decomposition. And if you compare this to the values we got for t, s, and a, and the top equation, you'll see that it works. So what have I actually done here? I've created an expression that if I added this all together, if I worked out the answer into a single fraction, I would get the original problem. We've essentially reversed that process here. Here's another example. I don't need to do long division because the denominator is a higher degree. Notice the denominator is third degree. And I don't need to factor my denominator because that's already been done for me. So I'm going to set up my decomposition. Notice I pick different letters every time. That's just for variety. It doesn't matter what letters you pick as your constants. Now, to clear my fractions, I'm going to multiply by the original denominator. And a lot of stuff cancels out. This may be a good time to hit pause, despite me having said I wasn't going to say that. And at this point, I am in my same position again, where I have to plug in random x values, or maybe clever x values, in order to solve for t, d, and l. I think one clever x value would be -1, because look at all the cancellation that would happen. I would have a t times 0 times something, and an l times something times 0. Now, when I plug -2 would also be a good choice because of the number of 0 factors that would create, and 4 is also a good choice, as you might have imagined. Now, again, without showing tons of algebra, in fact, showing no algebra whatsoever, except stating that it's there, we eventually solve for the constants t, l, and d, and ultimately have our decomposition of the original problem. Here's one more example. Notice this time the denominator has 3 identical factors, x plus 1 times x plus 1 times x plus 1. When you get 3 identical factors in your denominator, you have to set up your decomposition with varying powers of x plus 1. So you have to have a cubed, a squared, and a non-power or first power x plus 1 factor. Strange as that may seem, mathematicians have discovered this is how you have to set up powers of factors. So now to clear fractions, I'll multiply the whole equation by the original denominator. Convince yourself that this is what happens. Hopefully you paused, and now that you're convinced of that, we're back to plugging in values for x again. Now I think the first obvious choice is that -1 would be a great choice for x because of the number of 0 factors that would create. And when we chose x equals -1, the algebra, not shown here, leads to a value of -4 for t. And next I plugged in 99. Again, I don't recommend that you do this, but I'm trying to make the point that this really comes down to when there are no good choices, pick something. Maybe 0 is a better choice than that. But I wanted to make a point here that you can, if you ever find yourself in an seemingly unsolvable situation, you actually aren't necessarily in that. So I'm going to plug in 99 and 98 just to show you that even when things go bad, you can recover. You see, neither of these two equations, neither the middle nor the right, is solvable numerically for A or C because each one of them has a C and an A in it. But if I were to take those equations, I could solve that as a system. Now I'm not going to do that. I'm going to pick slightly smarter values here. When I pick 0 for x and -2 for x, I get this. But this would have worked for 99 and 98. But to make life a little easier, I picked 0 and -2 just to keep the numbers small. No particular reason or anything special about those. But still, I'm in the same situation. I have two equations, neither solvable for C nor A directly. So I can put those together as a system of equations. Now this video is not about systems of equations, but presumably if you're here, you know how to solve systems of equations. Ultimately, algebra not shown, this system of equations has c equals 2 and a equals 1 as its solution. And so now that I have the values of a, c, and I had already gotten the value of t, I now have my final decomposition for this fraction. Here's another example. Notice the numerator has a higher degree than the denominator, so I have to do long division. By the way, even when they're equal degrees, you must do long division. So I did my long division. Here it is. Feel free to look up videos on long division to get the details, but let me maintain the bigger picture here. Assuming you know how to long divide, I've now decomposed this into a non-fraction expression plus a fraction. And now I'm going to concentrate only on that fraction expression for the moment. So I'm going to factor my denominator, set up my decomposition. Now this setup is kind of strange. Check this out. I think it's clear where the x minus 3 came from, but why do I have an x and an x squared? Well, it's because I have a power of x. And just like we saw earlier in the lecture, when we did this problem, when we have a repeated factor, x squared being x times x, we have to have a decomposition that has one of them squared and one of them not. And so now to clear fractions, I'll multiply the whole equation by the original denominator. Again, good time to hit pause. And once you've convinced yourself that this is the result of clearing fractions, we're back to our normal plugging in x values routine, and it's just a matter of choosing wisely. I think choosing 0 is not a bad idea. Why 0? Because I'll have an s times 0 and a w times 0 squared. Anyways, we're late enough in this video where the algebra is not important, but d does turn out to be 2. I think 3 is a great choice for x here, because I'm going to have an s times 3 times 0 and a d times 0. In other words, the d and the s terms are going to cancel out, leaving me with some algebra that will ultimately lead to w being 6. And finally, there aren't a lot of good choices left for x, so no matter what you pick, you will get s is equal to 3. And now notice I have decomposed the fractional portion, but I have to include the negative x plus 3, which came from my original long division, as part of my final decomposition. And as we close this video, it's worth saying, if you didn't notice, that this video is heavily dependent on your algebra skills, your ability to clear fractions and solve for x and pick random numbers and plug them in. And so after having seen this video, I can't really say that the typical student would be super confident in their ability to do this process. So what you're going to probably end up having to do, practice some problems, and come back to this video, re-examine parts, and hopefully you'll piece it all together and be successful at partial fractions decomposition. And thanks for watching.